let's start. So yeah, I'll close this. Yeah, hope everything will work properly. Yes, so I'll take. So today I'm going to tell you about how machine learning can be applied to process neuroimaging data. Actually, the machine learning component isn't, I wouldn't say that it's the main one, because with neuroimaging data, you have a lot of different other challenging problems that you need to solve before getting any results. So today I will first of all briefly discuss the main concept of machine learning and discuss some challenges and describe some examples of neuroscience data processing. Before going into details, so just a very brief introduction. In Skoltia, I lead a big team of researchers. We develop procedures based on machine learning deploying for predictive analytics and computer vision, in particular for medical imaging. We collaborate a lot with industry and publish on different conference venues and machine learning journals. So, what's going on? Yes. So this is the agenda of today's lecture. That's it. First of all, let's start the presentation from discussing possible data sources. So actually, we can apply machine learning only if we have appropriate data. And in case of neuroscience, the data can be collected from MRI sensor, EEG. By the way, this big device around the person, this is a special shield to protect from external electromagnetic fields, so that the collected data isn't noisy. Otherwise, it will be very noisy. Also, of course, eye tracking, and there exist some special procedures when you collect data about the electric activity of the brain, exactly from the brain during the surgical operation. But mainly we will discuss today MRI and MRI. Okay, yeah. That's it. Again, these are the main data sources. Today we will mostly concentrate on MRI and MRI. First of all, let me discuss something about neuroimaging peculiarities. MRI, how we collect MRI depends on the specific medical protocol of medical examination. Each MRI is a three-dimensional image. So here you see this is only a slice of an image. And this is a very high dimensional observation, because each image can contain up to 10 to the power 6 and even more voxels. Moreover, in case of MRI, there can be different modalities which differ in terms of contrasts. So in one modality, it is easier to see some specific anomalies in the brain. In another modality, it would be easier to see other specific anomalies of the brain. Another type of neuroimaging data is functional MRI data. Functional MRI is a sequence of three-dimensional images. So here, in case of MRI, we measure contrasts, whether this is a white matter or a gray matter. And in case of MRI, functional MRI, we measure how the blood goes into specific areas in the brain during when a person performs some specific tasks. So if you are reading, or if you are thinking about something, different parts of the brain will be activated, and so in different parts of the brain the blood is concentrated, and you can detect this through a functional MRI. And so in each separate three-dimensional image, you can see which part of the brain is the mostly activated thanks to the thanks to the concentration of the blood at a specific moment of time. And so you get a sequence of high dimensional images for different moments of time. Neuroimaging data is very, it's difficult to collect. It can be quite noisy. In case of MRI, as I already told, it can have different contrasts. And the quality of data you collect significantly depends on the medical protocol. In case of different medical protocols, you will be able to extract different types of information from MRI data. Moreover, fMRI data is especially noisy due to various magnetic fields, magnetic fields, imperfection of the MRI device, thermal noise. Also, when we collect this data, the person can move even slightly, and this also introduces noise in measurements. And so it's important to somehow to denoise the data. In summary, we can have different types of data about brain, and different types of data bring different types of information. Like in case of MRI, we can get very high resolution and understand very accurately what kind of geometrical peculiarities a brain of a specific person has. And in case of fMRI, the resolution is significantly lower, but we have resolution in time. So we can understand what parts of the brain were activated when a person was solving some specific task, some specific mental task, or the person was asked to move his or her eye, whatever. The data is noisy, and all data modalities reflect brain structure function from different perspectives. And so this types of data is usually considered together by a doctor or researcher to fuse the information from different sources. Now let me, let's imagine that we collected this data. Now the question is, what kind of problems we can solve based on this data? So these are the list of problems. First of all, classification problems. So we classify whether there is a specific illness or not. Also, mapping and localization tasks. And in this case, we will be trying to identify specific regions in the brain responsible for some functions, for some specific functions. So today I will provide you with examples. And of course, relation tasks. This is the case when we have a lot of different, characteristics of a person, and also different characteristics of his physical conditions. And we somehow would like to connect these different types of characteristics and understand which characteristics depends on which characteristics. Of course, all these problems we can state a clear formal mathematical problem. Okay. Before going into details these specific applications, let me briefly, describe the general pipeline, the general idea of machine learning. Of course, it's not possible to do this in 10 minutes, and moreover, it's not possible to make a rigorous introduction. So I will mostly use some general concepts and figures. Sorry for that. Guys, so imagine that we have some objects like a human, a bird, or a house, and each object is represented by some specific features, characteristics. And the problem is that we would like to construct an algorithm which takes as input these characteristics, like a vector of numbers, and it should predict which specific class the object belongs to. Like if we have an image of a bird, we extract somehow characteristics that will significantly correlates with the class which we call class of birds, and we would like to be able to classify for a new image that, okay, whether it is an image of a bird or not. Let me provide a very simple example. It's an example from another domain, a business related example, but I think it's very easy to understand. So again, this part is only for those, is mainly for those who are not more familiar with machinery process. So the idea is as follows: imagine that you are the owner of an insurance company, and okay, you already have several offices across Moscow, and you would like to find the best place for a new office. There are several possible places for the new office, and which one is the most profitable? So we would like to predict that if we put the office here, or if we put the office here, what profit we get from that. And based on this prediction, we will select the best possible place for the office. What kind of data we can collect? First of all, we can collect demographic data, so like average age of citizens living close to a possible location of an office. Dynamics of number of citizens, property, whether property around is expensive or not, number of schools, shops, distance to the closest office of a competitor, insurance company, average number of cars passing by. So all these different characteristics actually influence the profit we can get. And so these characteristics are organized in a vector of some dimension. All these characteristics are organized in a vector of dimension d, and of course, in order to do this, we involve some subject domain experts, and also we, for offices which are already working, we can estimate their historical profits. And so we collect a sample, trained sample of inputs and outputs. This is a sample characterizing historical information about offices which we already have. And besides that, we also need to define loss function. So loss function, of course, we can control only what we can measure. And so loss function, it estimates accuracy of our prediction. And it's very important to define the loss function depending on the problem we solve. Because, okay, in case of this problem, prediction is that we get, imagine that we predict that we get $10,000 and the real profit is like $5,000. Is this good or bad prediction? Because we significantly overestimated the profit. Well, maybe this is good, maybe this is bad, but the answer depends significantly on the subject domain. And so loss function should correspond to real world requirements, depending on whether it's business application or medical application. What is the main idea which lies behind the machine learning models and methods? Actually, it is a so-called compactness hypothesis. That is, closed objects should have similar characteristics. Imagine that we have fruits, and we characterize each example of a fruit, like say peaches, peaches and apples or whatever. We characterize by two parameters: shape, characteristic, and color. And two types of fruits actually can be divided in terms of this characteristic in two-dimensional space. So we can construct some separated boundary between the two classes. And we expect that if we get new measurements with characteristics values of which are close to the values of the examples from the training set, then we have this high probability. This is, for example, an apple. But of course, if some observation is far away from our observation, well, maybe this is an outlier. And so, in order to realize this method in practice, we need to define the metric space, we need to define how we estimate distance given these features characterizing objects. And And also, and when we do this, we of course can construct a classification model. So the idea is it could be very simple. Imagine that we have apples and oranges, and we have a new observation, which is here, and the closest objects from the training sample in terms of characteristics are two oranges and one apple. And so it's it's very reasonable to say that okay, a new object with such characteristics with high probability is an orange because the most close objects are two oranges. So this is the most frequent class representatives from the training sample close to our new test object. This is the main idea, and of course, we can construct the idea of closeness, estimate distances using different, different tools from mathematics. So there exist different types of machine learning models. For example, decision trees. It's another approach. For example, we would like to make a decision whether we would like to work or we would like to have a dealer. And first we check whether it goes around, whether is good or not. And depending on this, we make a decision. And so the decision tree algorithm is based on this, kind of this type of thinking. But of course, inside it, the number of such divisions, the number of edges and nodes, it can be like thousands and even millions. And such decision trees in real practice, they are constructed automatically, and the final model is combined as an ensemble of different decision trees. Another important class of machine learning algorithms is based on deep neural networks. So let me remind you that here, in this example, for example, example about where we would like to put an office. Here we expect that we have some feature describing a possible location of an office. And the only possibility to get these features is to make some consultations with subject domain experts, so that a person who knows this business very well, the person tells you that, okay, it's very important that the average price for the property should be high, and because of that, you should put your office in that place where the price of property is high. So this is the most important feature, characterizing whether you get high profit or not, depending on other parameters. But this is only possible. This work is only possible if you can do this work only manually. And the question is, can we somehow automate this? In case of specific types of data, this is still possible. Now it is possible in case of images, sounds, and texts, so that we don't need to construct features manually. We can construct features automatically. And this is how neural networks work. So they extract from different scales of an image different types of features. This feature extraction is based on convolutions. And then through a sequence of linear and non-linear transformations, we transform these features into prediction of a specific probability of a specific class. So this is how deep neural network works. And nowadays, and you see that here, we don't make any assumptions on what types of objects are located on an image. We just construct a sequence of linear and non-linear transformations from specific classes and tune parameters of these transformations based on a very big sample of images with labels, labeled by so we need a sample of labeled images to tune the parameters of a neural network. And why neural networks are so popular now? It's because using neural networks, we can solve some specific classification tasks with a very high accuracy. For example, the task of classification of objects. In case of standard approach, machine learning approaches, when we extract features of images manually, if we would like to classify a cat or a dog, the overall accuracy in 2006, average accuracy was about 0.6. And so if we would like to classify cat or dog on 12 images, because the accuracy for one image is only 0.6, the overall accuracy of classifying of 12 images is almost zero. But nowadays, using deep neural networks, we can classify whether it is a cat or a dog or an image with accuracy almost 1. And so for 12 images, the accuracy is still high. And because of that, the captcha, a serial captcha which existed in 2006 to prevent you from, so we should detect whether you are human or a robot. This captcha doesn't work anymore because again, we can easily break the captcha with deep neural networks. And with deep neural networks, we can easily solve quite unusual tasks. For example, we can process an image using a sequence of linear and nonlinear transformations, and then using extracted features, we can predict specific, predict classes of specific words. And if we train such system properly, the resulting sequence of words, it will compose a sentence describing what is depicted in the image. So this is quite unusual. Standard machine learning approaches can't do that. And because of that, deep learning is very popular nowadays. But of course, deep learning cannot solve all problems. That's it. This was a very, very brief introduction, visual introduction into machine learning models. So in case of neuroimaging data, we need first to collect data. Second, we need to preprocess data to remove noise. Then we need to extract features, like we did in case of the business-oriented problem with locating insurance office. So in case of brain, we do the same thing. We extract some features characterizing different parts of the brain. And then we apply some classification technique or regression technique or whatever to predict whether this specific patient, whether the patient is normal. And now let me briefly describe each of these steps. What are the challenges in case of your EVG data for each of these steps? And also, let me provide you some examples of real-world problems. Because actually, a real-world problem, it doesn't contain reduce only to some classification task or regression task or whatever. Actually, contains often a lot of other different steps for which you may need complex mathematical approaches. First of all, denoising. So denoising is quite important because this is so-called low-level preprocessing. So this is the first step when you obtain the data from your imaging device. The second thing is what kind of information actually we get from your imaging data. As I already told, in case of your imaging data, actually the data can be represented as a set of time series. So each time series, it actually characterizes the activity of a specific points in the brain, of a specific region in the brain. And so fMRI data is a kind of set of multidimensional time series. For multidimensional time series, you can make a lot of feature engineering. You can construct correlation matrices between time series. You can construct a graph which it describes how time series depend on each other. For that, you can use both correlation, or you can use entropy, for example, mutual information to estimate whether time series dependent or not. Besides that, we can describe braid using not only this time series data, but also we can estimate volumes of different regions. In terms of feature engineering, describing a braid, you have a lot of different options. Okay. And the next step, as soon as we construct features, we apply machine learning algorithms to detect the objects of interest, to recognize detected objects, to find relations between the objects, etc., etc. And actually, as I told, there are a lot of problems and challenges. Of course, it's not possible to understand this table from scratch, but I will make the slides available after the lecture, so who's interested can look into more detail. But the main idea of this table is to explain that if, for example, the sample is collected from different MRI devices, then the statistical properties of the different samples are different. And so if you train your machine learning for prediction based on one sample and apply that machine learning to another sample, the accuracy of the machine learning model can drop significantly. It's because the statistical properties of a new data sample is different significantly. As I told, the data is noisy, etc., etc. So these different challenges, to some extent, can be solved when we use special machine learning approaches. And like in 5 minutes, I'm going to describe what kind of approaches can be used, just examples, and describe the responding real-world problems. Any questions so far? So maybe we can make a short break and guys. That's okay? Not too fast? I can talk slower.
Yeah, thank you. You mentioned in the very last sentence about the problem about different sets of the scanners. Like, for example, one part of the sample was collected on the one type of the scanner and the other part was another scanner. Do you know how maybe solve this problem? Maybe try to project this data to the same domain or to some data space and to solve this classification type from that. So basically, how to solve the problem that you collect on different sites. Thank you.
Okay, thank you for the question. So actually, this is a very great question. Currently, there doesn't exist, unified approach to solve that dimension problem. In case of image processing, there exist different approaches which are called domain adaptation or transfer learning. And these are exactly approaches how you can compensate that domain shift. So if your training set differs to some extent from the test set. However, and of course, people try to use these approaches for medical data. In some cases, it works, in some cases, not. And so, unfortunately, there is no unified approach. So, like the tool which is accepted by everybody. So, in some cases, I would say that there exist several heuristics, and there will be one of examples later in my presentation. Okay, because in the very beginning of this presentation, I told that it's very important to consult a subject domain person, because that person should tell you what are the main requirements to the solution. And this is even more important in case of medical applications. And so, in this case of medical applications, we cooperate with different medical research medical centers in Russia. These are some examples. The first example of data analysis is about noise elimination. So this is a project developed by my colleague Maxim Sharayev. And so, as I told you in the very beginning, there can be different sources of noise, like cardiac noise, respiratory noise, and others. And most of noises are assumed to be independent from signal and from each other. This is a very important assumption. And there is a very well-known problem in signal processing and data analysis called cocktail party. So cocktail party problem, it can be formulated as follows. You have a big room like here, and there are a lot of people here who are talking. And we collect the signal of these talks, which are mixed. And we assume that, okay, all people are talking independently, and we would like somehow to process that one-dimensional signal in such a way that we can decompose it into independent signals of different people saying something. Under some, of course, the problem is opposed, but under some assumptions, in particular, the independence assumption is the most important one, it is still possible to solve the problem. And so we use exactly this approach in case of eliminating noise from MRI measurements or fMRI measurements. So fMRI measurement, as I told, it is a multi-dimensional time series. So we have a multi-dimensional time series signal, and we assume that, okay, that multi-dimensional time series is a mix, like linear mixture of some other multi-dimensional time series, which is responsible for real signal, and some other multi-dimensional time series which is responsible for noise. And so we can apply, and in a minute I will show you the formulation. And so we can apply this, and here is the result. So let me just show. So what we do, you see that here the brain even changed its position, and here it doesn't change its position. It's because here, in measurements, there was a signal which was induced by moves of a person lying inside the fMRI scan. And so it was so-called movement artifacts. And when we decompose the fMRI signal into components, and remove one of the components, and then compose the signal back, we get this result. And when we extract the noise, when we delete the noise, according to experiments in some tasks, this can improve accuracy of classification up to 5-20%. Another important part, when we analyze fMRI data, it is related to, as I told, it's related to pitch extraction. So fMRI data is can be represented as a multi-dimensional time series. And so one of possibilities how we can, compress these data is to construct a graph. So this is the matrix characterizing. So each element of this matrix, it is equal to some coefficient which estimates the dependence of a specific time series component on another specific time series component. To estimate such coefficient, we can use correlation, we can use visual information, or we can use or other statistical measures of dependency. And so this graph, it represents how different parts of the brain depend on each other. In my second talk, I will be, by the way, describing some approaches how we can apply machine learning to graph data. In particular, I will show how we can use so-called anonymous walks embeddings to represent graphs and classify depression and epilepsy. But another thing what we can do with these graphs is to apply so-called topological data analysis. I don't want to go into details, but this is a funny example. So we got some data from hospital, and here we this is some kind of how the Betti number depends on the radius, the threshold with which we specify the corresponding graph. And it turned out that for one patient, the fMRI data was corrupted, and some of time series values here, they were equal to 0. So we just noticed that. And these logical characteristics for the patient behave like this. So it's a clear outlier anomaly. And when we saw this picture, we realized that the matrix calculated for this fMRI time series, it looks like this. So it's a clear anomaly. Quite unusual application of anomalies of topology-based characteristic for communication. As I told, we can represent the fMRI data as a graph, but also we can represent the fMRI data using directed graphs. To estimate directions, we can use different approaches. For example, we can use transfer entropy, which measures deviation from equality. Actually, nowadays there exist already approaches how we can construct persistent diagrams for directed graphs. And using this, we can extract features from persistent diagrams. And in principle, this can improve further accuracy of classification. So analysis of directed graphs is a quite interesting possible research direction. Now let me discuss some real-world applications. The first application is about the first application is about fMRI data decomposition for presurgical planning tests. The idea is that, so imagine we have a patient with glioma, and before performing a surgical operation, we need to plan the surgical operation. A person has specific parts of in the brain, centers responsible for speech, for movements, and it's very important when we remove glioma, we shouldn't destroy these centers. Otherwise, the person won't be able to move or to talk, which is very valuable. But for different persons, the positions of these centers are different. And so, before doing the surgical operation, we need somehow to identify where possibly these positions are located in the brain of a specific person, which can help to plan the surgical operation. Of course, during the surgical operation, so-called operative cortical simulation mapping is done. This is when the brain is, the head is opened, and they wake up a person, and they has a special device. This is it. And so here there is some electricity in it, and when you touch a specific part of the brain and ask a person a question, if you touch a part of the brain responsible for speech, the person cannot speak. But if not, then the person can speak. And all this not very pleasant thing is done during the operation when the person is waking up in the middle before removing the group. Of course, this invasive procedure should be to some extent minimized, but it's not. It cannot be removed because this is a golden standard, and only thanks to this integrative cortical stimulation, we know where we can understand where the these centers responsible for speech and movements are located. However, at least before the surgical operation, we can use task-based functional MRI. So what we do, we put a person into MRI, and we ask a person a questions. So the person answers, and we can see which parts of the brain are the most activated. And so we can see these places. However, if the patient is not in good condition, even such procedure is quite, energy consuming. And so another possibility is to use so-called resting state functional MRI. That means that we just put the person inside the fMRI scanner and that's it. So this is so-called resting state fMRI without any tasks. And so it turned out that the signal we observed during resting state fMRI, it is composed of signals which go from the speech center, from the visual center, from the movement center, and from other parts of the brain as well. And so if we you apply a special variant of ICA, so again, ICA is when we observe some signal X, and we assume that this signal is a mixture of components of the signal S, and we assume that signal components of the signal S are independent. And so we would like to construct the inverse mapping so that we estimate these independent signals. In case of our problem, these are signals which comes from visual, from movements, and from speech centers. And so the idea is as follows: we construct the we obtain the resting state of MRI. We apply a special type of ICA procedure to decompose the signal, and then we can identify different signals, those signals, and correlate them to some specific regions in the brain. In this way, we can identify that region in the brain which is responsible for speech, for example. Okay, I'll skip the details, I think. Yeah, and so currently we are testing this procedure. For that, we developed a special visualizing capability. So we can use this capability to label data. We can use this capability to visualize predictions made by this procedure based on ICA, etc. Okay. And now let me discuss classification tasks. The first classification task is, the first classification task is about applying generative models for knowledge transfer. This is the paper with my colleagues. So they were the main driving force of this approach. MRI segmentation. So imagine we have an MRI, and we would like to automatically to construct a neural network that can help us automatically segment some problems in the brain, so that we apply it to process MRI images. The standard neural network to predict semantic labels of, say, glioma, it is so-called UNet, for example. So it is a sequence of linear and nonlinear transformations, and as the output for each voxel of an MRI image, it predicts whether there is glioma in the voxel or not, or whether there is some specific problem in the voxel. The challenge is that the data is scarce because to train the model we need labeled data, but it's very expensive to get labeled data because good doctors, they are always busy, and so it's difficult to find a person who can professionally label data. In order to, and so in this project, we developed an approach based on generative models that can help to, to use the model trained on one data set and transfer that knowledge to another data set. So in this part of the presentation, I'll skip the most of technical details, but okay, still I'll try to discuss the main idea. First of all, what is a generative model? So generative model is a special model that takes as input some simple distribution, say a Gaussian distribution in a low-dimensional space. Using that simple distribution, we can generate a sequence of random vectors. And then there are special approaches, and I'll tell you about one of them today, that we can construct a neural network model which takes as input this low-dimensional vector and produces output through the sequence of linear and nonlinear transformations a tensor which actually represents an image. And so that means that if we properly tune coefficients in this nonlinear model, various convolutions, coefficients of convolutions, and other coefficients of these linear and nonlinear transformations, as output we can generate a set of images randomly. It's because, and this is possible because real-world observations, they belong to manifolds. That is, you can think about the manifold as a some nonlinear surface because actually parameterized by a small number of parameters. It's because the features of real-world observations, there are a lot of dependencies, and so actually they don't, real-world observations, they don't fill the whole d-dimensional space. They are located in some small parts of that space. And thanks to this distribution here, we use some distribution of this space of object descriptions, for example, images. So this is the ideal generative model. And one of specific examples of generative models, they are called variational AutoEncoders. The idea of the variational AutoEncoder is as follows. We take as input some image. We process that image using neural network so that it returns as output. So this encoder, it acts not like this, so it acts like this. It takes an input image and produces as output some low-dimensional vector. And so this low-dimensional vector, it parameterizes distribution in the lattice space. Then from this distribution in the lattice space, we can generate a low-dimensional lattice vector again and transform it using the decoder. And here, this is exactly the decoder. And we tune parameters of the encoder and decoder in such a way that as the output of the decoder coincides as accurate as we can with the image which we use as input. And so we collect a big sample of images and we train parameters of encoder and decoder in order to get the accuracy of reconstruction as high as we can. And how we can use such generative model in our case. So when we train this unit on some specific task, for example, the task of glioma segmentation, inside this unit model, there will be coefficients of filters tuned for this specific task. However, these coefficients of, and so the parameters of these filters, they are not random numbers. They depend on each other because they are tuned for this specific task of processing MRI data. And so filters of a neural network tuned for a specific task of medical image recognition, they belong to some manifold of filters corresponding to medical tasks in some respect. And so the idea is, if we train a neural network successfully on some problem, we can extract filters from this neural network, get a sample of filters. We construct a manifold of filters using this sample of filters and, for example, this kind of neural network. And then, when we train a neural network with a new sample of medical images, we do this under the restriction that coefficients of this new neural network should be restricted to that manifold of filters. So we take into account the dependencies between coefficients, and this helps us to, to take into account the knowledge from the previous task. And because of we take into account the dependencies between coefficients, this we don't need a lot of data for the second problem, for a new problem to train the neural network, because we take into account the dependencies between coefficients. And so the overall pipeline is as follows. We train a network on some source data set, we collect filters, we train implicit prior distribution, for example, based on variational AutoEncoder or based on generative adversarial network. There could be different variants, and recently we developed the approach based on the generative adversarial network. And then we use the trained prior to perform the construction model on the model construction on the second phase. Let us consider an example. We have a sample of multiple sclerosis, and so we train the first neural network to predict these tiny anomalies here. The second problem is about segmentation of brain tumors, and so we would like to train the second neural network on a small number of brain tumor images as possible. And here is the result. The first neural network was trained on 170 images, scans, and of multiple sclerosis data set. And so the accuracy was quite good. Then we extracted filters from that network, constructed the manifold of filters, and trained the second network under the assumption that the filters belong to that manifold of filters. At the same time, the second data set contained only 5 images, so very, very small, but still, this is the result of the test sample. This is the input image. This is the labeled image, so this is the ground truth, the target which you would like to predict. This is the prediction by our model, trained only on 5 images, plus that restriction that we need we shouldn't deviate too much from the manifold of filters, and this is the predictions of standard models. And so you see that the accuracy is quite high, even in case we use a very limited sample. Yeah, that's it. I think I still have some time. Another challenging, problem with all these medical images is that we can have samples of different fidelity and labels of different fidelity and modalities. So here's an example. Imagine that we would like to segment some specific tumor or anomaly in the brain. And actually, first of all, these images can have different modalities. For example, different contrasts. And in some cases, you can have all contrasts. In some cases, you can have only one specific contrast. because in practice, the real world samples, you know, they are quite uh, not uniform, I would say. Moreover, the labels in the training data set, they also can be of different type. The label can be semantic, like here. The label can be in form of the bounding box, or you may not have a label at all. You can have only the label 01 that, okay, this patient has a tumor, and this patient doesn't have a tumor. That's it. And of course, this type of labels is very expensive to get. This type of labels is less expensive to get, and this type of labels is not so expensive to get. And so you can expect that you have a lot of labels of this type, you have less labels of this type, and you may have quite big number of the labels of examples with labels of the third type. And so your machine learning model should be able, your algorithm should be able to adapt to this inhomogeneous data. Okay, I'll skip the details. If you want to see the details, you can read this paper. We constructed some architecture of neural network that is able to take these ideas into account. And here is the result. So by red, we depict the label provided by a radiologist. And this is the model which is trained only if we use semantic labels. So we use only these labels. We don't use the labels of this or that type. And this is, and so we see that here we have, I would say, false alarm. Here we miss, so red is a real position of a tumor, and blue is a prediction. And here we missed, so we didn't predict the tumor, and here there is no tumor and we have false alarm. So the accuracy isn't that high because the sample size isn't big. But if we take into account these less accurate labels, the accuracy of prediction increases significantly. So we predict, we make correct predictions for all test cases. Okay, this example, I think I'll, but still I still have them, yeah. And the third example is about mapping and localization task for detection of electromagnetic activity. So here the problem is that so we do this project with Glakov and Pirogov, medical research centers, and the problem is that some humans, some patients have the epilepsy, such type of epilepsy that cannot be treated with drugs. And so only surgical operation is possible to cure the person. However, we need somehow to identify a specific place in the brain that is responsible for the epilepsy. And actually, 45% of people with this epilepsy are MRI negative. And so it's difficult, that means that it's very difficult for a non-professional radiologist to understand this based on MRI data, that okay, this person has some specific, region in the brain. It's a very small region in the brain, where, say, the depth or contrast of the gray matter is too high or too low, or maybe the width of this region is too high or too low. So there are some anomalies, and because of those anomalies, electric activity is to some extent distracted, in the brain, and so the person can get epileptic, case. Can get suddenly an epileptic, problems. And as I said, for non-professional radiologists, it can be very difficult to identify such places. Moreover, we can observe only two-dimensional slices of a three-dimensional image. We cannot see the structure of the brain, in three dimensions on a screen, on the two-dimensional screen of a computer. Because of that, it's difficult to identify the anomalies, and actually, many of these anomalies can be not correctly identified, and that is why the success rate of surgical operations is quite low. Here is another example. So you observe that, okay, here this region is not, the width is a little bit higher, and because of that, the person has problems. Or, for example, here. And the question is it possible somehow to construct a kind of second opinion that can help the radiologists to identify, pre-filter some possible places where the problems can be, to help the radiologists not to miss something important. And so currently we are working on this. The first step is that we constructed a software that can help to visualize various modalities and various view angles of MRI scan. This is actually the brain, but we just, how to say, pump it so that all these, structure is removed, but we represented this structure with a color. And actually, what we can do, we can depict some possible deviation from normality using this color map in a very simple way. We calculate average characteristics of an average person, or even we can calculate average characteristics in some local region for a given person. And then we compare these local characteristics with the actual characteristic in a specific place. And depending on this, we use a color to depict that, okay, here we have some significant deviation from normality, from some average values. Based on this signal, we already can analyze that there are some problems. But actually, what is important here is to develop the machine learning model that is able to process such three-dimensional data. So the neural network should somehow feel the structure, the shape of this gray matter, white matter of its surface, to understand that there are some anomalies in characteristics and curvatures. And currently, there exist special architectures of deep neural networks which are capable to process signals on meshes and on point clouds. So we are developing such architectures. We are tailoring such architectures to process data in this application. That's it. But besides the classification, also I mentioned relation tasks, but I'm not going to devote a lot of time of my lecture to it, to do this type of tasks. So relation tasks, as I told, is quite important to understand how a person educates, how, for example, in China currently is very popular to try to develop pipelines for personalized education. And for example, a startup Squirrel AI from China it got a significant funding from USA for these approaches for personalized education that takes into account different characteristics of a person. And one of such characteristics can be actually physiological parameters of the person. And with colleagues from Paris School of Economics, we are processing their data. These are data collected when a person is performing some solve some tasks, some simple tasks, or not so simple, and they measure first of all eye tracking. Also, they measure as a result of eye tracking, we get such trajectories, and we can compare different people by these trajectories. So this is another quite challenging task because the data we have to process it is represented as a two-dimensional trajectory of eyes, and so we want to relate different properties of different such physiological characteristics with performance indicators of how the person's whether the person studies efficiently or not. So this task is ongoing. That's it. As a conclusion, I will say that neuroimaging data has a lot of interesting peculiarities. Standard machine learning pipelines are not well suited to process such type of data because the data is very rich in terms of structure, like three-dimensional shapes. You can represent data as graphs. You can represent data as images. You can represent data as multi-dimensional time series. Because of that, you have to use different modern mathematical tools, even topology, differential geometry, all these statistical learning approaches in order to get good results. Otherwise, standard approaches from machine learning like extract features in predict from scikit-learn using Python, this doesn't work. That's it. Questions, comments? Questions? Yes, please.
Oh, thank you very much. And in cases when you have such small data sets, you try to use a fast or training.
Well, this is a good question. Yes, in principle, we are trying to apply any possible, possible tool from modern machine learning that could help. We try to use neural networks to train on some different data sets. Currently, there exist data sets from Wikimedia, for example, and human Clinical project, where there are thousands of MRI images of which you can train the neural network. And then you can tune it for your task even in one of the examples I provided an approach how we can perform transfer learning from one data set to another, and the size of the second data set was very small compared to the size of the first one.
Yes, but it's 170.
Yeah, and of course 170 sounds not very deep, right? But it's not that not on the one hand, yes, but on the other hand, here we were solving the semantic segmentation problem, and averaging, in some sense, the averaging of the loss function is done not only with respect to the number of images, but also it is done with respect to the number of different pages, because, okay, segmentation neural network, it moves across the whole scan, and this can be also considered as a kind of average. And so, because of that, for semantic segmentation problems, in case of medical images, even more or less limited sample sizes sometimes work quite.
Thank you for the lecture. Can you you tell more words about your work with Betti numbers?
Unfortunately, yes, sure. Unfortunately, right now I don't have here the ready to show slides. Currently, this is more or less, currently, this is more or less ongoing research. So I would say that we have ready to use pipeline or ready to use procedures that about which we really believe that these procedures are very efficient. We test, so the idea is very simple. We have some fMRI data. For this fMRI data, we can construct, we can represent the fMRI data as a graph. Actually, we can introduce filtration for the graph because, actually, the graph it originates from this matrix where each number of characterizes the dependency between some specific time series, right? And so, of course, we can introduce some threshold, and by moving this threshold from, say, 0 to 1 in this relation, we can get either fully connected graph or disconnected graph, right? And so this is a natural filtration. So because of that, we can calculate persistence diagrams. For that persistence diagrams, we can calculate some features and use these features in an ordinary machine learning pipeline to predict something. Sometimes this works, sometimes it doesn't work. Moreover, in many cases, the results are not better than if we use some standard graph features. So I would say that in case of medical applications, we were very happy about the efficiency of topological descriptors. Still, maybe it's because the samples are too limited, maybe it's because we don't use appropriate topological features. Maybe we finally get some bigger sample and use, say, persistent diagrams constructed based on directed graphs. This will work better. Who knows? We are sure that topological data analysis is quite good for comparing manifolds, and we in my archive you can find the paper about that. And but this is about real other types of data like images, point clouds. But for medical data, still, I would say that I really found an application where topological things are very who knows? Maybe one day we will find some.
I suppose that in such as field as medicine, your clients ask you to explain your models. Do you use any methods for explain how your network works, sharp line?
Yeah, this is a very good question. And so the answer is actually, unfortunately, there is no clear answer, in the sense that the application of machine learning for medical data analysis is still quite, I mean, especially deep learning is still quite young, in the sense that the methods for model interpretability are quite well developed in the general field of machine learning. Sorry, I'm just trying to find the slide with the list of features. Yeah, no, not this slide. A second. Yes, yeah. So the topic of interpretability in general machine learning is more or less well developed, especially if we consider the case of input features, some meaningful input features. But in case of medical applications, this is not true. Of course, if our machine learning model is based on some vectorized features, for example, various volumes, curvatures, thickness, which we estimate for MRI scan, then it's easy to interpret the machine learning model because, okay, we use sharp values for sober indices or whatever sensitivity indices we like. And okay, if we understand that the volume of a specific brain region, this feature, the model is very sensitive with respect to this feature, then it's very easy to explain to the doctor, right? But if we apply a modern neural network, of course, we can apply some modern methods for interpretability to this deep learning model. However, in order to check whether your interpretability results are meaningful, you need to consult the doctor, right? In case of standard applications, you can be the expert who say, okay, this is a very reasonable results of interpretability methods, right? But in case of medical applications, we need to consult some other expert. And this often takes a lot of time. And because of that, I would say that in the medical domain, there are a lot of successful applications of modern methods of machine learning interpretability. So maybe this is a good venue of the future research, for future research. Currently, we are investigating this. We have just started, but
okay, more questions? Some small question for myself. You consider the filter manifold. What kind of information do you need from this manifold? For instance, is it essential to consider correlation with filters or something like this?
Okay. Yeah, so actually, I mentioned that in this application, when we train a neural network on a specific task, the filters of the neural network, these are not just random numbers, but we clearly see some structure in values of this field, of these filter coefficients. And so somehow we need to model this dependency. Of course, we can use a linear manifold like PCA manifold. We just take these filters, consider each filter as a sample point, and train PCA, principal component analysis, on these filters as a sample. In this application, we used a nonlinear model, which extracts somehow nonlinear correlations between these values. In what exactly correlations I don't know, because the model is based on deep learning, and so it's quite difficult to interpret.